Starting with the name of Allah, the most beneficent and the most merciful. Myself, Dr. Fahad Rasool. I'm serving as Associate Professor in the Department of Agronomy, University of Agriculture, Faisalabad. And today I'm going to talk in this conference. I was very much wishing to participate in that, but due to several engagements, I'm not able to participate. Then I thought that there could be some virtual participation to interact with all of you. So I will be talking about climate change impact on rice productivity. This is my title: Assessing the Production Sustainability of Rice Genotypes to Thermotemporal Variations by employing the modeling techniques. The climate change and rice crop productivity, this is very important relationship that rice, which is is a major crop, and it is very important part of our life, that all the events of our life, either any happiness or any death, there is serving of rice. So rice is very important, and more than half of the population of the world is dependent on that. But this crop has been subjected to the vulnerability of climate change too much. So we will be talking about that, the various types of rice, how they are being affected. So climate change and rice crop productivity, the temperatures above 33 degrees centigrade at anthesis has caused pollen sterility in rice, and thus it has decreased the yield. There are various reductions in grain yield have been found depending on the stage of rice crop. So different crops have different rice has shown different type of sterility and sensitivity to various stages, the phenological stages of that. The cultivar susceptibility also varies. There are various cultivars are responsive to climate change, and some are not responsive to climate change. The leaf area index, net assimilation rates, and paddy yield, these are reduced by the late transplanting of rice. So timing of the rice transplanting is also very important. It is good to analyze that we have the tools, especially the crop models, that can be used for assessment of these rice yields, that how the climate change is going to play with these rice varieties. So climate change is definitely with the help of tools like crop modeling, um, we can assess the impacts and how much they are going to affect different crops. And in this case, which I am presenting today, that is to study the impacts and adaptations of climate change on rice productivity. Crop simulation models are used as agronomic tools. Definitely, it's a big tool, and we are from several years we are using this tool to assess the climate change impacts. And this tool, especially the crop modeling tools, and important one in these scenarios, there are various models, but DSAT, the CN support system for agro-technology transfer, is among one of the major package of work that has been employed and being studied all over the world. And in this DSAT system, the CSM CERES-Rice is one of the important tools which is being used for assessment of rice yield prediction in throughout the world. The objectives of our study was to investigate the impact of temporal changes on rice productivity, and to assess the performance of CERES-Rice model for simulating the growth, development, yield of cultivars under different sowing dates, and to evaluate the different adaptation strategies, that how we can go for the sustainable rice production in the future climate. Uh, So I will be talking about in detail about all of these. So we designed actually three different kind of experiments, because there are major three different rice categories grown in Pakistan. One of the most important, that is the fine rice type, the Basmati type of rice. And we chosen two different varieties of Basmati, the Basmati 515 and Super Basmati. These are two famous and more stable and highly cultivated Basmati varieties. And we tried to study them through the transplanting at various transplanting dates. So we grown these number at these different nurseries on different timings and so on. For each of the nursery plantation was of 1 month old, or you can say 30 days seedling were sown, were used for transplanting. So for each of these transplanting dates, as mentioned here, you can see that the first transplanting date was 2nd May, then 17th May, June 2nd, June 17, and every 15 days or 2 weeks, you can say, we grown rice to estimate that how various transplanting dates, and on those transplanting dates, the weather, temperature conditions, atmospheric conditions, how they are going to affect the rice varieties, and we'll see it further in detail. So there were three groups. One is this Basmati group, the other is coarse rice group. In that we chosen two different varieties, KSK 434 and KSK 133. These are also the KSK stands for Kala Shakaku. So these are two different varieties, 133 and 434. So these were also shown on in a parallel experiment in different days, starting from 2nd of May up to September 16. In the third experiment, we chosen two different hybrids. These two hybrids were RH362 and PHB71. These two are from two different multinational companies, and their hybrids were used in that. And they were also grown for different sowing dates starting from 2nd May up to September 16. So crop modeling was we used the DSSAT version, or you can say CSM CERES-Rice version 4.7. During this experiment, we noted down the weather data which was collected and the weather observatory from University of Agriculture Faisalabad. The soil data was obtained from Soil Survey Department of Punjab for Lailpur series of Faisalabad. This is about the soils. Historical weather data of last 30 years from 1980 to 2010 was recorded for baseline, and that data was gathered from Pakistan Meteorological Department, Mehkama Mausamiyat, and then model was calibrated with the best performance with best performing treatments. Here you can see the estimated genotypes coefficient of CSM CERES-Rice during the calibration. So on the left hand side you can see the varieties Basmati 515, Super Basmati and other, and in this column you can see that the different genotype coefficients P1, P2R, P5, P2O, G1, G2, G3, G4 and FINT. So these are various genetic parameters that are mentioned below here. Thermal time for emergence, critical photo period for the longest. So these are genetic characters, that how varieties are responsive, how much they are photo period tolerant, how much they are sensitive to the flowering, and likewise. So these descriptions are here, and those people who are related to modeling, they understand it easily. So these genotypes were estimated. Then calibration of the CERES-Rice model for fine rice was performed, and then you can see that in this calibration that was very well performed, and in the observation 84 days, after 84 days there were antitheses, and simulated was also 84. Likewise in the Super Basmati 82 and 83 there was very close, so differences were almost negligible. So this is the fine tuning for the model to perform in the later stages. So firstly this calibration was done firstly for fine rice, and in this slide you can see that the same kind of responses were noted for coarse rice, and the anthesis date in KSK 434 variety, that was 74, and the differences was 0. Leaf area index maximum was 5.88, 4.9, and there was some slight variation, and 15.14% was the difference found. And similarly, quite similar or fine-tuned varieties were calibrated for coarse rice in KSK 133. And then came the hybrid rice. The calibration shown that the anthesis stage came earlier as compared to the other one, the late varieties like Basmati. And anthesis stage in RH362 hybrid, 67 days observed, 68 days for simulated varieties, and likewise you can see here the difference, that is very minor difference, except for leaf area index that was maximum 17.87% difference. So there was variation. And the evaluation and validation of CERES-Rice with fine rice variety Basmati 515 that was performed under different transplanting dates, and the results shown that the anthesis date, maturity days, and leaf area index maximum, then paddy yield and biological yield, these were calculated. The DSSAT values for them, these were all in the normal range. For the RMSE, root mean square error, you can see these 2.365, 2.339, and so on. And in 2015, you can see quite similar trend is observed. And super basmati varieties, they were also evaluated and then validated for certain calculations, and this is the data for that. Then coarse rice varieties, these were also evaluated and validated for the different transplanting dates. And then KSK 133, these are the values for different years. For 2014 and 2015, these are the model results. And here you can see that the paddy yields in kg per hectare in 2014 and in 2015 there were differences in paddy yields. And for hybrid rice, you can see a clear-cut difference of that. In 2014, 1490 kg per hectare was the yield for paddy yield was observed in 2014, while in case of 2015, that year, the 1622 kg per hectare were observed or recorded. And for the other and for hybrid rice PHB 71, there was not so big difference that in the yield, 1308 and 1371. So you can see that there are several variations among varieties, among the sowing dates in different scenarios. The input data set that we used for models, that was historical data of 30 years, was used for climate change analysis from 1980 to 2010. The temperature, solar radiations, rainfall, atmospheric CO2 was taken at 360 ppm. And then future data was generated using GCMs, the general circulation models, under representative concentration pathways 8.5. The RCP 8.5 were used for the mid-century, like for 2040 to 69, what could be the impact in the mid-century scenarios. And then statistical downscaling were performed, and then selection of suitable GCMs were carried out. Future climate projections for mid-century 2040 to 69, you can see here that climate change projection was generated using the GCMs for the latest CEM-IP family under RCP 8.5 scenario, where the CO2 concentration rose up to 571 ppm. In that scenario, this concentration of CO2 is 571 ppm. And the 5 GCMs were selected because only one cannot be relied upon for general circulation model. So 5 different GCMs were selected, and different models, they projected different things. The 5 possible climatic characteristics were cool and wet, cool and dry, hot and wet, hot and dry, and middle. Middle means the medium one. So the monthly changes in mean, maximum, and minimum temperature and precipitation by comparing future 30 years climate periods to the current 1981 to 2010 climate period were observed. So the climate data of historical data was used from 1981 to 2010, and for projections of 2040 to 2069. These monthly changes were then imposed on baseline climate in the analysis using using distribution approach. The relative changes in temperature and rainfall under all GCMs with respect to their baseline were observed for mid-century scenario, and here you can see that the baseline or current scenario in that the maximum temperature was 37.66, and in the middle scenario the maximum temperature will be 41.16. That will be, the change will be about 3.5 degree centigrade. In the hot wet scenario with the GCM IPSL CM5A, the maximum temperature will be 39.33. That will be, from the baseline it is a 1.67 degree increase. In the hot and dry scenario, the GCM CMCC CMS, the maximum temperature was 41.29. This is the highest one, and 3.63 is the maximum temperature that is expected. In the cool wet scenario, the GCM CESMI BGC, this predicted that the temperature maximum can rise up to 39.10, and the variation in maximum temperature 1.45. The cool dry GCM represented that 40.61 is the maximum temperature. Yes, this is the highest one. No, sorry. 41.29 is the highest. This is 40.61. And likewise, the changes in minimum temperature and rainfall is also given here, and the maximum rainfall variation is in the second one, the hot wet scenario. The 248 mm rainfall is expected in, more is expected in hot and wet scenario, and minimum rainfall change was observed in cool and dry season scenario. And the averages are also given here, that maximum temperature is 2.64 variation, and 3.35 is the minimum temperature variation. Simulation results. Here you can see the quantification of climate change impacts on rice production during 2040 to 69 through crop models under 5 climate scenario, how this climate change is leading us on the way. So here you can see through the box and whisker graph that this is the yield graph, and you can see in 2040 69 the fine rice how it will be changing. The first one scenario is here is shown as, this is being shown as this green one. This is the baseline scenario, and you can see that in the hot and dry, this is also is producing less yield compared to the baseline, and hot and dry has more yield decrease compared to the baseline. Then cool and wet, this is comparatively near to the baseline. Then cool and dry season, that has been represented here as for fine rice. Typically the cool and dry weather has performed better, and could be the scenario that it is almost near to the baseline. In the hot wet scenario, yield reductions are possible drastically, and in the middle scenario there will be slight decrease in yield for the baseline scenario. For the coarse rice, the baseline is here shown in the green one, and there will be severe decrease in the hot dry scenario. There will be comparatively less decrease in the cool wet, and here you can see for the other ones. For the hybrid rice scenario for 2040 to 2069, you can see the baseline there is drastic decrease, and all of the models are showing a decrease in the yield for hybrid rice. So that shows the sensitivity of hybrid rice to the future climates. Then we tried the adaptation models. Then we used the various agronomic managements, that how agronomic managements can help to curtail the effect of this changing climate. Those predicted agronomic through RAPs, the regional, the representative agricultural pathways. The soil fertility could contribute up to 8% positively towards the yield. Increase in the amount of urea applied, that can increase 15% positively to that. density of the planting density can change up to 8% in the yield scenario. Then water holding capacity, if can be improved, that can improve the 10% yield. And likewise, the organic matter, that is also very important, the soil organic carbon or organic matter, that is that can increase up to 10% of the yield. So these are the agronomic adaptation possibilities that we can apply for the future generation, for the future of the climate, for the future adaptation packages. There could be some breeding option that through breeding we can improve, if we can possibly improve the CO2 response, that can add up to 10%. The heat or temperature tolerance up to 2 degrees centigrade can impact positively, and thermal time of about 8% increase can impact positively. Radiation use efficiency of 8 to 12% can impact positively. Likewise, grain weight can be improved, and if 10% grain weight can be improved, that can impact positively. And photosensitivity is also very important, that need to be reduced, or we can say that for the breeding options, 15% less sensitivity will add more to the yield. Yield improvements for fine rice after RAPS, the representative agriculture pathways. Here you can see the change in the scenarios after the adaptation package was applied. And here you can see from the baseline, there will be in hot and dry, it will be still less yield. In the cool and wet season, fine rice will be performing better after adaptations. In cool dry also, it will be higher yield than the other ones. For coarse rice, there will be a mixed kind of trend, and from baseline, hot and dry will be less. It is also was the same in fine rice, but in other it will be not so much so much drastically varying, except the hot wet, which shows the drastical yield decrease. And for the hybrid rice, after the adaptation package could be applied, then from the baseline, hot dry will be of course reduced, because hot and dry both conditions are not suitable for rice. But for cool and wet, there will be improvement in rice yield for hybrids as well. In the cool dry season and other, there will be in the cool dry and middle one, it will be almost in the same range of the baseline. And in hot and wet scenario, hybrids will have reduced yield. The potential agronomic adaptations to mitigate climate change impacts, from our results, that could be possible, that we can adapt to the in the directions of change. We can have the sowing dates, the transplanting of rice 5 days earlier than the current recommended sowing date. That will increase 2% of the yield. The nursery age of the transplanting age, earlier we used 30 days rice seedling, so instead of that we can use the 25 days old seedling. This could help increase in up to 3% of the yield. The fertilizer rate, if we can increase that by 10%, then from the current recommended rate we can get a 7% increase in the yield. With the improvement on planting density by 20% more plants in the field, we can get 5% more yield. Similarly, irrigation amount, if 15% reduction in irrigation amount, then 2% increase in yield is possible. So here comes the conclusion of the study. The fine rice transplanting time, that is first and second week of July, and the coarse rice or hybrid rice transplanting is mid-June, is suitable for that. Hot and dry conditions, that means the more than 3.63 degrees centigrade increase and reduction of 80 millimeter rainfall are threat for rice in semi-arid climate like Pakistan. Climate change may decrease paddy yield 10%. So the climate change has a big threat to decrease of paddy yield from 10% to 64%. This is the variable range that have been found out, that during the mid-century scenario for 2040 to 69, under RCP's 88.5 scenario, there will be this drastic decrease of 10% to 64%. The agronomic management can increase the yield by 20 to 35%. So there are possibilities that we can adapt to this climate change. So our recommendations are here that optimum time for transplanting of fine rice is first fortnight of July, and for coarse or hybrid rice this is the first fortnight of June. And the climate change impacts can be reduced further by agronomic adaptations like modifying the transplanting dates to few days earlier sowing time. uh, Planting density can be improved and nursery age could be reduced. Fertilizer rate maybe we need to increase more, but even in these days, like, there is fertilizer crisis, but still that is an option that we can use more fertilizers to cope with the threat of the climate change yield reductions. And this paper has been already published. These data or the details of this research can be found out by searching climate change impacts and adaptations for fine, coarse and hybrid rice using CERES-Rice. This data was published in the Environmental Science and Pollution Research. Thank you very much, and here was the sponsors, and we belong to the Agro-climatology lab. And I guess that for question answer, maybe Dr. Habib can also support me for questioning and answering, and I would be available for any question or answers. Thank you very much for your attention.